So rates of change are now exponential function, very commonly done with growth and decay questions, those sort of questions. And the growth and decay starts with a very simple assumption, simply this, that the rate of change of the population is proportional to the population. So in other words, it's equal to some constant times the population. It kind of makes sense. I mean, the more people you have, the more births that are going to happen. The less people you have, the less births that are going to happen, things like that. But if you remember back to yesterday when we were investigating how do we differentiate the exponential, and we came up with, for e to the power of x, that the derivative was equal to the y value. In other words, the y dx was equal to y. Have a look at this equation. To p to t is equal to some constant times p. There's a pretty good chance that our exponential is going to be a solution to this. Our solution will end up being some constant times e to the power of some multiple of t. We just got to work out what those constants are, and then we've got the formula. Here's an HSC question. 10 years ago now, eh? The amount of caffeine in the human body. So C is representing the amount of caffeine, and they've given us that, what we call a differential equation. To C to T is equal to negative 0.14 C. So the first thing we can conclude is it's decreasing. Even though they told us that, from the equation we can see it because our rate of change is negative. So it's got to be decreasing. C is measured in milligrams, T is the time in hours. And sometimes what they do is, instead of asking you to solve the equation, they'll give you a solution and say, look, show that this is a solution. So rather than having to go through the calculus to show that question, I can simply substitute in and work this out. So if C is equal to AE to the minus 0.4t, well, when I say without calculus, I'm still going to differentiate, but I don't have to start with the C to T. I start with the given equation and differentiate that. Differentiate our exponentials, what we saw was we differentiate the power. It's just negative 0.14. So we end up with negative 0.14 AE to the minus 0.14t, but that is minus 0.14 times what C is. So yes, it is a solution to this differential equation. Now when T equals 0, we know there's 130 milligrams of caffeine. Work out what A is. When T equals 0, C is 130. That's what they've told me. Therefore A, and what we can now see is, well, hang on, if T is 0, e to the power of 0 is always going to be 1. So that constant out the front will always be the initial value, which in this case is 130. So A is going to be 130. Right? Well, how much is now in the body after 7 hours? It really just becomes a substitution question now. C equals 130 e to the minus 0.14 times 7. We bung it into the calculator and we get 48.8 to 1 decimal place. So that's how much caffeine we have. What's the time taken for the amount of caffeine to halve? C equals 65 then. Well, that's a half of 130. Again, it's a substitution question, but now I've got this exponential equation to solve. And to undo the exponential, we log both sides and we end up with this. Now, you might recognize the form of this solution. It's the same form as, say, when you're finding the half-life of radioactive material. Because essentially that's what we're doing here. We're saying, when is there half the amount of caffeine? It's like the half-life of the caffeine. So it's always going to be some constant times the log of a half. And that constant is minus, because it's decreasing, 1 over the 0.14, that rate of decay. That turns out to be 4.95105, so on, so on, so on. So about 5 hours. It takes about 5 hours for it to halve. That finishes the theory for the term. Okay.